alloy single crystals. So you will get these slides. So for every lecture, I put on the first page some kind of outline and list of papers where you will find the details on what I did said. Hopefully you have the access, and the most important ones will come along with the lectures, so you will have these papers included.
These lectures and slides will be given to us?
Yes, yeah. Well, hopefully I didn't say something too early, but yes. Including the copies of the papers which are listed here. So, yeah. It was like how much? Almost 30 years ago. In our lab, So it was like 30 years ago when I entered this Institute of Physics. It was the laboratory where researchers investigated the dislocations in iron-based alloys, the dislocation slip. And there was a man called Václav Novák who has been doing that for something like 20 years. And one day he said, we are doing that too many years, let's start to do something else. So he came with the idea to grow the single crystals of copper, aluminum, nickel, and try to investigate the processes in these materials due to the Martensitic transformation. So the first part of the work, the growing of crystals, tend to be pretty easy because it's very easy to grow the copper, aluminum, nickel single crystal by Bridgman method from the seed. So we were happy, we had samples, we could make the samples for tension, for compression. And the another beauty of this research is that because it's strain reversible, so with one sample you can make 30 tests, and basically you can make one paper with 30. And but we were not the first. There was already a group in United States by Professor Wyman and Otsuka and Miyazaki who did experiments, basic experiments on copper-based alloy single crystals and discovered all this kind of Clausius-Clapeyron relationship and the hysteresis. So most of the properties were known. And so what could we do with that? If you make the tension compression test on the copper, aluminum, nickel single crystal, it looks like this. So in tension you have one transformation, then you increase the stress and another transformation, and if you unload you go back like this, and in compression you have this like that. There were not many people around the world who did this. And if you change the orientation of the crystal to maybe you will obtain a completely different response. And if you change the temperature at which the test is made, again different response. So Václav realized that it would be nice to map the stresses and temperatures at which this transformation occur over here, independence on temperature and orientation of the sample. So this means to do a lot of tests, but because with one sample you can do a lot of tests, you can obtain such kind of maps, and the map look like this. So this is stress, this is tension, this is compression, this is temperature, and maybe here at room temperature you have this transformation, which would be this one. Then you unload, you go back, but it also depends. Okay, like for each transformation you have two lines. One is forward, one is reverse. You know? So for example here you have only this line, so up and down, so it is here. But if you load more, you will have another transformation which is about at this stress, about 700 megapascal, which is this line. Now, so we developed the methodology how to find out the transformation stress temperature condition for each of these processes which occur in the material. It is clear. We could also see on the surface the moving interfaces. So on the stress strain curve we can see the plateau. So this is the stress at which transformation proceeds. By optical microscope we could see the trace of the interface planes, and because we know the load axis and orientation of the crystal, we know the orientation of the plane, habit plane. So we know everything about the system. And this was not known. For example, if this would be a forward and a reverse transformation. So if we look into the papers published at that time, they always put the transformation here into the middle and call it like equilibrium. This is the equilibrium stress or equilibrium temperature. But we put the forward and reverse, and this is the advantage here is that we really know at which stress it occurs. From the equilibrium, you know it also, but you have to use the hysteresis width, and this concept doesn't work very well. So very soon the mechanical engineers who tried to develop the models, they started to like these kind of non-equilibrium diagrams, because they are like, if you have this diagram for 5, 6 orientations of the crystal, you know everything about the system. You know also the orientation dependence. So we did such kind of research. I was a PhD student at the time, working together with Václav Novák. This was the in situ taken pattern which we could see on the surface. So this is forward transformation, and reverse is practically, it looks very similar during the reverse transformation in tension. In compression, it is here. So this is in compression. So in compression we have one transformation, but then the other came, and there was one interface which erases everything, and if we unload it remains there, this martensite. And upon heating, this was the structure there, but upon heating it was completely different. So at the time we didn't really understand this kind of patterns which were observed upon heating, and until now this is not really understood, because if you imagine here, this is austenite, then there are these plates, and then they are consumed by this gamma prime martensite, and here the martensite is oriented and is in the gamma prime, and you start to heat it. So it wants to go back to the original austenite, but there is no habit plane. The nature doesn't allow for any habit plane between this gamma prime orthorhombic martensite and austenite. So what happens is that, I hope it will work now. Yeah. So you see one interface moving and second interface moving behind. So the first interface was interface between oriented martensite and twinned martensite. But there is no driving force for such process. You cannot heat the specimen and expect that it will twin. This is, for theory, this is completely unimaginable. But it exists. We have seen it here. And in other cases, here the sample was deformed only 400 megapascal. In other cases, we deform it up to high stress, like 1000, and then we heat it, and when we heat it, the sample jumped to the ceiling. Because, and again, this is the problem of this habit plane. The martensite is deformed, completely oriented, there is no habit plane, and somehow this process which you see here didn't start, so we were overheating, So we were heating maybe up to 150 instead of 50, so there was 100 Celsius overheating, a lot of energy supplied to the system, and the reverse transformation occurred very quickly, dynamically, and because of reaction it jumped to the ceiling. Yeah? So these processes until now are not really understood. Recently I was reviewing some article doing the analysis of those kind of things, which is very now because they were observed, and we were not only one, the others observed as well already 30 years ago, but the understanding of those phenomena, it has nothing to do with plasticity. The sample is undamaged after that. Yeah? It all has to do with how the habit plane, strain compatible between the austenite and martensite is created upon heating. So, well, we published a series of papers. I do not have to go to the details, but maybe a few comments are worth to say. So, you know, the hysteresis, if you have such transformation line, this is temperature, this is stress. So if you do the cooling, heating under stress, this would be the hysteresis with something like 50 Celsius for this beta to gamma prime transformation. So, this diagram clearly explains that the phase transformation is induced, also can be induced by stress. So if you have temperature and stress applied simultaneously, you have to combine them together to create the driving force on your system and compare it with the volume fraction. So the transformation is inherently thermomechanical, so be very careful that if you try to formulate like a hysteretic equation, you always have to have driving force expressed using stress and temperature. And then so in other means, like in the people who develop the mechanics models, they are used to work with temperature like a parameter. But in shape memory alloy, the temperature is a driving force equally good as the stress, like we have to look at the hysteresis always as thermomechanical hysteresis and compare this driving force with psi, and then everything is fine. Yeah? So most of the models, of course, respect this, but very easily, if you do the particular investigation, you can very easily make a mistake. You see something like 15 degrees hysteresis, but hysteresis is not 15 degrees. Hysteresis can be 100 degrees if you calculate it properly as a thermomechanical one. And again, in these materials, they are very, very strong. The dislocations practically do not move. Yeah? So we have these conditions that all processes which we see in those tests were really only due to the Martensitic transformation. So we are absolutely sure that we have this Ericsson-Pitteri neighborhood respected, and everything is fine, and one can develop the models for this system. But if it's not respected, we are in trouble, and this is the case, unfortunately, with nitinol, which I would say later on. So this is how these diagrams look like, and then much later on, I think around 2000 something, we needed like a small cube single crystal for ultrasonic experiment. So Václav started to work, and the time I was out of the, well, I already came. We started to work with compression test on those kind of cubes. So I said again that in copper-based alloy you have austenite. In case of cubic to orthorhombic transformation, you can make six variant of martensite, and the challenge was, can we make them by compressing this austenite cube? And the answer was yes. we could, even though this is on the surface, it looked kind of strange, but after we did some experiments on it, we were able, using one cube, to make 1, 2, 3, 4, 6 orthorhombic variants, so we could make a single crystal of martensite. It was a big success because for analyzing, for example, elastic properties, you need martensite single crystal, but at that time we used so-called pulse echo method, so you have to propagate the ultrasound around specific direction, but for that you need a specific single crystal. And if it can exist in 6 variants, we could make, by compressing here and here and here, we could make these 6 variants and then analyze it. So the result was very nice. And these pictures which I already shown come from those experiments. So when we compress the cube, frequently we have 1 or 2 or even 3 processes before we arrive to the final single crystal.
Is it the dimensions of these cubes?
This is like 5 millimeter. This is like 5 millimeter, this is like 0.1 millimeter. But this is only a small part of somewhere here.
Do you use any special utensils to compress it, or what is the equipment you use to do this?
We compress it in instruments. Yes, you have seen that the single crystal cube becomes prism, like this. So if you put it into the instron machine, you would like to allow for this motion. If you don't allow for this motion, how you make a prism from the cube? So we started with some kind of special grip which had a sliding part, but then we realized this is useless. It's enough to oil it a little bit, and if you oil it, because the force which makes the crystal to go into the prism is very high, so when we pressed, it went to the prism. So you just press and it goes to. This is the beauty of the Martensitic transformation, because the transformation is connected with this strain gradient, and strain gradient prescribes the cube to become this prism. And then these faces are parallel, so if you press like this one, it will go to another one, and another one, and another one. And in the paper, there is methodology how to do it using two strain gradients. You know? What we wanted to investigate was the orientation dependence of twinning processes. The problem was that like if you, for example, have a crystal and some process occur at 20 megapascal and some at 100 megapascal, when we compressed, the 20 megapascal occurred before, and it never reached the 80. So even if we calculated at which stresses should be the second process, we were not able to reach it because, as you see here, you know, because the first process occurred. But the final aim was to get the single crystals, and we got the single crystal. So this is comparison of the curves. We published the article about the orientation dependence of twinning, and later on, when people started to work on this nickel manganese gallium system, when they need to explore this kind of low stress twinning, they use this knowledge from our experiment, how to cut the crystals and how to deform them to be able to utilize the ferromagnetic shape memory phenomena using this low stress twinning. So, and basically it's very, very similar in nickel manganese gallium and in so this is again the part of this strategy, but I don't think I have to go to the details. It would take lots of time. Very interesting is what happens if you just have a cube and then you cool it to the martensite. So you will have the microstructure like this, which is a jungle. No one knows. So we wanted to know how this will be converted into the single crystal. And then if you look at it, it was very, very simple. Suddenly the interface came, somehow oriented with respect to this kind of jungle, and erase it to the nearly single crystal. There is some laminate. So this laminate was necessary to create this habit plane, and upon compression, after this disappears, also this one disappears. So the material, everything is controlled by this habit plane compatibility. At the time when we did the experiments, I didn't understand it very, very much. But later on, when we investigated the same processes in nitinol on the level of nanometer, it was the same story. So we realized that this is actually the same situation. Everything that can be described mathematically by putting the shape strand related with two kind of twins and these phenomena. So for the material, it's relatively easy to create the interface between this jungle and laminate. Yeah? And after this disappears, the laminate will disappear as well. So it's only a matter how it goes there. Okay. Well, another thing which we didn't understand that one. One day, the Václav came and told me, look, I made a bicrystal. So by trying to press, suddenly he pressed and he couldn't erase neither this nor that one, because the crystal became, you see how it's like a book, open book. Yeah? So there is an interface between two laminates of martensites, and now if you press on it, because they are symmetrically related, you cannot continue this process. And so we were puzzled how it can be that there is such kind of interface. But the reason is the same. Even this is the interface in the material, and the strain compatibility at the interface must be fulfilled. So when we compressed, the material deformed in such a way that the strain at this interface became compatible, and this is the reason why he could make the bicrystal. And recently I looked in the nitinol into like a 20 nanometer grains, and I look at the traces of 001 planes, and they look exactly like this. All of them were in a mirror shape, because the interfaces between them were strain compatible. So physically it was the same phenomenon, but here it was on the millimeter scale, and in nitinol it occurs in nanometer scale. Is the same. Made by a friend of mine, Michal Landa, who worked in the nearby institute, and he developed the ultrasonic method to analyze the elastic properties of the material. So when we had this kind of single crystal constant, we thought, okay, let's work together and measure for the first time the elastic constant of orthorhombic phase in copper, aluminium, nickel. Unfortunately, one day, 5 years or 4 years back, he didn't come. He was working at the computer in the night and got a stroke, and it's no more. But he was an excellent guy. He had a very good PhD students who now continue his work. So at the time we started to develop the pulse echo, which was well-known, well-established method for characterizing elastical properties, which I will talk about it now. But this is a sort of history, because the team has continued to work in this direction. So we built the laser-based ultrasonic system, which if you have now we are enough. Okay, for this one we need 6 single crystal cubes, but for resonant ultrasound spectroscopy, 1 cube is enough. It's like between two grips between the corners, you know, the cube is like this here, and then you excite and measure the vibration by laser, and from the oscillation of the specimen you can determine the elastic properties. And then you can have this with the changing temperature, so you know how the elastic properties of martensite and austenite are changing with temperature. It's a beautiful system, very nicely made, and it is now in the lab. So if anyone of you would like to measure the elastic properties of some single crystalline material, the sample could be like 1 millimeter cube, no need for 5 millimeter, very small one. We can evaluate the temperature dependence of elastic constants, and this is very useful information, as you know, for the material engineers. So the Michal Landa was a world-renowned expert in this field. One article of him, it's ultrasonic methods for ferroelastics, like for piezo and so on, where you have the system where you have internal interfaces. Of course, this method requires a single crystal. So, but some materials exist only in case of lamellar infrastructures, which can even move. Then the ultrasound propagation is a problem. So, but he developed the methods for testing such kind of lamellar materials which have internal interfaces inside. Okay, but let's go back to the history. So this is the analysis of single crystal material. Again, it's in the article. I will not go. So in TUS experiment, what do you measure is that you measure the orientation dependence of the velocity of ultrasonic wave which propagates in austenite and one martensite variants. So from this you can construct something like a velocity map in 3D space, which is this red space. So you find out that in some directions the ultrasound propagates very fast, in some directions very slow, and from that you can understand, you can calculate basically the elastic constants, and you can somehow understand how the austenite behaves elastically. And if you make the same for martensite, which is here, which is this blue surface, you will find out that actually there are, you can fit two kind of objects, which is the space distribution of the ultrasonic speeds on itself, that the minima are around the same directions. So this for me, this was something like the understanding how it comes, how the transformation from austenite to martensite proceeds, because you have the information how the vibrations of the system in the different directions are changing. And so this article was published something in like 10 years ago, and we could this is the martensite object, where there are such kind of volleys which suggest what kind of directions are weak direction in the martensitic system. So people can now understand based on this how the elasticity of austenite and martensite are changing near the transformation condition. It's for engineers it is more clear in the case of if you plot the instead of acoustic waves, if you plot the orientation dependence of the Young's moduli, so it will be the same object. Now red is for austenite, blue is for martensite, and you will find out that in some directions the maxima are quite similar, but in other sections it's very different. So here you have the minima again in both cases, and this is what I was talking about. This is the condition where the martensitic minimum fits the austenitic minimum. In nitinol the situation is very different, but I probably will not go more into the detail. What is more clear to understand here is this. This is what I mentioned, the temperature dependence of elastic constant. So what is known is that the C prime constant, which is kind of scales with the Young modulus in austenite, is dependent on temperature. So here, this is the C prime in austenite, and it changes something between 7.5 and 7, something like this. But no one knew what is how it looks like on the martensite side. And look on the martensite side. The C55, which in orthorhombic phase, which would be sort of comparable to C prime, changes like 10 times more. So frequently, because of the high symmetry, people know and study the elastic properties of the austenite, but they never study the elastic properties of the martensite. And the martensite behaves in a similar way. So if you heat towards the phase transition, the material extremely changes, softens. So at the transition, it becomes elastically extremely soft, and you have a very high damping. So if you of course, if you measure the damping ability of the material at the transition condition, it will be very, very high because of this, and also because of the moving interfaces, which adds to it. But this was the main result, of two sex.
That the Martensitic elastic constant will depend on variant reorientation.
On what?
Variant reorientation.
This is okay. The elastic constants are calculated for one variant orientation, and then they apply for any variant. This is the characteristics of the system. It doesn't matter. What matters is how the austenite and martensite are related together. Because I told you, in fact, there has to be a habit plane where you have austenite and twinned martensite on the other side. But now I don't speak about it. Yeah. So you have in reality you would not have austenite and martensite single crystal on both sides. You will have a twinned martensite here, and these elastic properties combine together on the side of the laminate. But this is not in this experiment. I have a martensite single crystal and I heat it. This is one variant. And here I have austenite and I cool it. It's another variant. So I don't solve this problem. It doesn't exist. But we assume that the single crystal constant are similar for all variants. They only combine together. Yeah. You can what I just said. You can even see it in the experiment. This is the measurement of this is how the strain changes during cooling heating, and this is how the wave velocity changes during heating and cooling. So why the wave velocity is changing? Because of changing of the elastic properties. And there could be, because it's under stress, there is no laminate, there is only one variant. Okay. And finally, the experiments which we did together was measurement of acoustic emission. So I said in the beginning today that about the sound which it generates. So we can do it scientifically. We can measure the sound by acoustic emission sensors, which was done in such experiments. At that time, we did it because no one else did it. This was the main driving force for doing such experiments, and we were quite surprised. For example, this was the acoustic emission during forward transformation and reverse transformation. So it was this kind of laminates, forward and reverse. If you look here, the forward very low, the reverse very high. But in the microscope, it looked kind of similar. Only we didn't know very much about the second phase over here. But there was a very big difference between the acoustic emission activity during the forward loading and reverse loading. We published that in around 95 something, and I have seen this many times again appearing without real explanation why it's happening. We also didn't, it was just part of our paper, but we were not able to explain this. It has to do something with this propagation of habit plane during forward and reverse transformation. It's not completely mirror same. It is now like interesting that if you apply the stress to the single crystal, then in macroscopic experiment you measure stress at some moment the transformation starts. Okay, but if you measure simultaneously the acoustic emission, you will find out the acoustic emission starts only here. But if you look on the surface, there are no laminates, no habit planes. The stress is increasing. You are in the elastic range, but the acoustic emission activity sharply increases over here. So what it is? Yeah, there is something. If you are straining the crystal, either it happens outside the field of view where we looked, or there are some nucleation events which occur, but doesn't grow. And the second explanation is probably the right one. So like this acoustic emission detects very early the onset of the transformation which is coming. You can also look at the elastic properties by wave speed propagation and attenuation. This is here. If you go above, you will find it here. So if we measure simultaneously the propagation of the ultrasound waves, and now we are probing the whole volume of the crystal, it starts to decline here in the middle of the elastic range again. And now you cannot explain it that you are not looking at the place where it happens. Now it is really the volume, a property which is relevant to the whole volume. So something is changing in the elasticity of the material, which tells us that the transformation will come soon. So this is here, and the same with attenuation, which increases as the wave speed is decreasing. So it would be good if we have. So then we started to say, okay, these elastic properties. This is a great tool to detect the transformation processes. And I will be talking later about it, but maybe I can say even here. What is great is that the acoustic emission comes from the whole bulk of the volume. And the same with the propagation of ultrasonic waves. You scan the whole volume, so you get the information about the whole volume, about whether the transformation starts or not. And the only problem is that to do it like for engineering materials, for example, there is a Griebel simulator for simulating the metallurgical processes. So you would like to have such kind of in situ experiment during Griebel simulation. And the problem is how to put the contact for ultrasound. And this was solved with laser ultrasonics in the last maybe 10 years. So now such methods, there is a Canadian company making and such kind of system in situ which can be used, adjusted to the Griebel, and they use the propagation of ultrasound to detect these kind of changes. But you can use it for many other things. For example, now in 3D printing, there is if the 3D printing is introduced on industrial level at companies, they buy like 50 printers and start the process on 50 printers. The problem is if something happens during the process, everything is spoiled. So some kind of in situ testing of the processes is necessary, and again the ultrasonic method is very useful and can be applied for that. And if you can activate and measure by lasers, everything is solved. So These methods are very useful. We thought we will use it for shape memory alloy, but we never did it because simply because this is the life.